Next, let's turn our attention to the ideal gas turbine cycle, also known as the Brayton cycle. Now, instead of using pistons and cylinders like we have so far for the Otto cycle and the diesel cycle, our compression and expansion devices will be steady flow devices. So we'll have a compressor and we'll have a turbine, a compressor for compression and a turbine for expansion of the gases. So the compressor will increase the pressure of the air that comes in at state 1 up to state 2, which also increases the temperature of the air. And then we'll have a combustion chamber afterwards where fuel is added to burn in the high temperature air, increasing the thermal energy of the air. That then goes into state 3, the entrance to the turbine, where the gases at high pressure now are allowed to expand through the turbine, producing work. Now, one thing about this, if you notice, the compressor is back driven by the turbine. Just like in the Otto or the diesel cycle, when the piston compresses the gases before burning fuel, that takes energy, that takes work. So in the same way, the compressor also requires work in order to operate, and that has to come from the work-producing device, which is the turbine. In a regular piston cylinder engine, the way things go is that a piston that is on an expansion stroke can be used to drive a piston that is on the compression stroke. So, and of course, the piston on the expansion stroke produces more work than the work required to compress the next charge of fuel and air mixture. So in this case, the turbine is driving the compressor, and there's enough work left over to extract work from this engine and have a net generation of work from thermal energy. Now, in the real engine, fresh air is pulled into the compressor and exhaust gases are tossed out of the turbine. That's the end of it. But we're going to use air standard assumptions, and so we're going to, in the idealized cycle, take the exhaust gases from the turbine, which would just be hot air, cool it down like the atmosphere would do, and then run it back into the compressor. Similarly, in the combustion chamber, well, rather than having a combustion chamber, we'll have a heat exchanger from state 2 to state 3, where thermal energy is added via heat to the air that's flowing through rather than an actual combustion process. So we end up with a transition from state 1 to state 2 across the compressor being isentropic compression, because again, it's ideal if the compressor operates reversibly, and we're assuming there's no heat transfer, so this would be an isentropic process. And then state 2 to state 3 is our constant pressure heat addition. Now you might look at this and say, well, wait a second, how do you know it's constant pressure? Well, there's certainly a significant change in pressure across the compressor and across the turbine, an increase across the compressor going from state 1 to state 2, and decrease across the turbine going from state 3 to state 4. But from state 2 to state 3 in the combustion chamber, that's essentially either a heat exchanger or an open system where fuel is simply being added to hot air and burning. So there's not much flow restriction. Now, in the real engine, is there flow restriction? Of course, there's some. But it's such a small pressure drop that we're going to neglect it and just pretend that the pressure is the same at state 2 and state 3, and therefore we've got constant pressure heat addition during this piece of equipment, this heat exchanger in the ideal situation. Then from state 3 to state 4, that's the expansion again across the turbine, and then finally from state 4 to state 1 is the constant pressure heat rejection in the external atmosphere, because you realize that if you're pulling in air in state 1 from the atmosphere, that's atmospheric pressure. You're tossing out exhaust gases in state 4 from the turbine, that's going also to atmospheric pressure, and so from 4 to 1, those are the same pressures. So one interesting note about this type of process, though, is that it's not as efficient as you might think it is. One of the problems is you're compressing a gas, right? So I really haven't pointed this out yet, but there is a significant amount of energy required to compress the air, whether you're using a compressor or a piston cylinder device or whatever you're doing, because you're compressing a relatively high specific volume fluid. Remember what we learned about steady flow work. We learned that the higher the specific volume of the fluid being compressed, the more work will be required to compress it. And so that's working against us in all of these cycles so far. And so one thing we're particularly interested in is what's called the back work ratio, and it becomes more apparent in this particular cycle, where work from the turbine, rather than coming out as work we can use for whatever we wish, it goes instead back to the compressor to just continue the cycle. And so if you see the graphic off to the right, you see the arrows there. The work produced by the turbine, some of it comes out as a known amount of work, but some of it has to go back into the compressor just to maintain the cycle. So The way we're going to quantify this engine, rather than a compression ratio, which doesn't really make sense here, we're going to use a pressure ratio, because if you think about it, the pressure at state 2 and state 3 are the same. They're at high pressure. The pressure at state 1 and state 4 is the same. That's a low pressure. So there's really only two pressures here to be concerned with. And the pressure ratio then is simply the pressure from the high side to the low side, so P2 over P1, or if you will, P3 over P4. They're the same thing. So that pressure ratio is something that quantifies the nature of the engine, just like a compression ratio in the auto or the diesel cycle. And we will quantify the back work ratio as the work consumed by the compressor divided by the total work produced by the turbine. Not the net work produced by the cycle, but the total work produced by the turbine. And this can be on the order of 50% or so very easily. So now at this point in your book, you should go find the TS and the PV diagram for the ideal Brayton cycle, and you'll notice that it consists of four processes, just like the other two so far have. State 1 to state 2 is an isentropic compression process, no change there. State 2 to state 3 is a constant pressure heat addition process, and that's very much like what we saw in the diesel cycle. State 3 to state 4 is an isentropic expansion process. We saw that in the diesel and the auto cycle. But now here's the one change. There's a constant pressure heat rejection process from state 4 to state 1. Now in the auto and the diesel cycles, both of those were constant volume heat rejection processes. So that has changed just a bit. Now notice there's been a logical progression where the heat addition and rejection processes are the only things that change. So in the auto cycle, those two are constant volume processes. In the diesel cycle, the heat addition process goes to a constant pressure process. And in the Brayton cycle, the heat rejection process then moves from a constant volume to a constant pressure process. So there is a logical progression from the spark ignition auto cycle to the compression ignition diesel cycle to the Brayton cycle that you can see. Now you'll notice that all three cycles involve compression and expansion processes that are ideally isentropic. Now of course how isentropic, how reversible these things actually are depend on the nature of the engine itself, how it's designed, how much heat is wicked away during these processes, and of course how reversible they are. How well do these devices perform in terms of reversible expansion or compression of the gases. It depends on the design. An engine with much more friction is going to be less reversible. You know, an engine that allows gases to expand quickly will be less reversible because it's more unrestrained expansion of gases. So just something to think about. Make sure you mark the TS and the PV diagrams because you will refer to them quite a lot in the class. Now, since we've changed over to where now we're dealing with pieces of equipment that have fluid flowing through them, now that fluid can have enthalpy, and so our energy balance will change to where we're not only dealing with heat and work interactions, but now we're dealing with the enthalpies of entering and exiting streams. So we're interested in the fluid power that flows through each of the various pieces of equipment, the compressor, the heat exchanger that represents the combustion chamber, the turbine, and then the heat exchanger that represents the atmosphere. We're going to use an isentropic equation to represent the compressor's performance. So that's from state 1 to state 2. We're going to use an energy balance during the heat exchange, the combustion process, to represent what goes on there. And notice here, since we have a flowing stream going through that combustion chamber, we have to keep track of the enthalpy of the fluid. Notice we've already neglected any kinetic and potential energy changes of the fluid in our energy balance. And that's valid for this Brayton cycle and the typical pieces of equipment you'd find in a gas turbine engine. From state 3 to state 4, we use another isentropic equation because it should be isentropic expansion ideally through the turbine. And then we'll use another energy balance through the atmospheric heat exchanger, the cooling down of the air before it goes back through the cycle. And again, notice that this is a steady flow thing, so the air has flow energy, and we have to use the enthalpy change of the air from entrance to exit of that heat exchanger. So now that we have all of these equations developed for the Brayton cycle, we're going to play the same game we did before and write down the efficiency and try to see if we can figure out what that efficiency really depends on. So we'll start with 1 minus the ratio of the specific heat flows. Plugging in the energy balance for the heat addition and heat rejection processes, we have something where the heat capacities now cancel again like they did in the Otto cycle, but this time it's Cp over Cp that cancels. And again, the algebra is not obvious, but we can work in the two isentropic equations for T1, T2, and T4, T3. Now, what's more interesting here that you should note is that we're not using the same isentropic equation that we used for the spark ignition cycle. We're using an equation that relates the temperature in the two states for the compression and expansion processes. We're using an equation that relates those two temperatures to the pressures in the two states. Since the pressure ratio is something we typically know for the particular designed engine, then this ratio, P1 over P2 and P4 over P3, is simply related to the pressure ratio, not the compression ratio, which is what we had in the Otto cycle, but instead the pressure ratio. And so we end up with an efficiency that kind of looks like the Otto cycle. The only difference now is that we've got a slightly different exponent. And of course, instead of having a compression ratio, we have the pressure ratio in the denominator. Now, again, if we look at this equation and plot the efficiency versus pressure ratio, what you see is that the efficiency increases with the pressure ratio. Higher pressure ratio means higher efficiency. Now, that's a good and a bad thing. As I said before, these engines are commonly used in helicopters, and so if you have an engine in a helicopter, let's say that is to save lives, right, a stat flight type helicopter, your focus is not so much on how much fuel the engine burns, although it needs to burn a reasonable amount, not be unreasonable. More interesting to you is the weight of the craft so that it can get off the ground, right? You want to have a decent payload in order to save lives. So having an engine that's high out on the efficiency curve isn't necessarily what you're looking for. Think about it. If you increase the pressure ratio, what does that mean? That means the pressure on the high side is pretty high. What does that mean? Well, just like in a diesel engine where you have high compression ratios, the more you compress the air, the hotter it gets and the more force that it applies to the components inside of the engine. And so the stronger the engine has to be. And typically what that means is that's so much more metal that you have to add just to provide that strength. Now, if you start making a very heavy Brayton cycle engine, you're going to quickly end up with an engine that won't lift a helicopter off the ground because the engine's just too heavy. So the highest pressure ratio for the highest thermal efficiency is not necessarily the best idea. Now, another problem is that as you increase the air temperature by burning fuel in the air, the components that the engine is made out of can only take a certain high temperature. As a matter of fact, about the highest temperature the common materials can take is about 1,000 Kelvin or so. Now, it turns out that the actual melting point of the engine components is typically higher than that. But if you heat up a metal to where it softens so much that forces can cause the blades to stretch, for example, then that's a problem, because most turbine engines turn at many thousand RPMs, even tens of thousands of RPMs. And with those sorts of centrifugal forces, there's a lot of force required just to hold the blade in place. And if the blade is so hot that the metal is weakening where the metal can creep and deform just due to the force that's required to keep it moving on a circle, the engine's going to fail. And so the maximum practical temperature with speeds and so forth is about 1,000 Kelvin or so. That sets the upper limit of the temperature. Well, it turns out that also let me back up. If you draw the TS diagram for the Brayton cycle or the gas turbine cycle, then really you're working between temperature limits on the y-axis. Now, usually use air for your working fluid, so it's going to come in at just regular everyday temperatures, around 300 Kelvin or so. Colder in winter, warmer in summer, but relatively close to 300 Kelvin. Certainly nowhere near 1,000 Kelvin. But that basically, that 300 incoming air temperature and 1,000 degree maximum temperature sort of limits the range of that TS diagram. As you increase the pressure ratio, what you're really doing is moving that diagram. So you'll notice on the right we've got a smaller sort of vertical column where RP, the pressure ratio, is listed as 15. Well, you'll notice this is a fairly small area that's enclosed. Okay, I wish I could point to this. Let me try with the mouse. Yeah, there we go. So from state 1 all the way up and then over to the high temperature line and then back down. This is a fairly small area, which means that while the efficiency is high because the pressure ratio is high, we just don't get much work out of this, right? So we have an engine that just does not produce a whole lot of work. On the other hand, if we take the pressure ratio way down where it's inefficient, we still don't produce very much work. So you see that the diagram is spread out here. And again, the area enclosed is relatively small. So there's sort of an optimum, a sweet spot for the pressure ratio that maximizes the area, in other words, the amount of work produced by the cycle, while giving us or offering a reasonable pressure ratio so that we don't have to have an engine that's overly bulky, that has too much material in it. So as I said, a lot of times what we care about is not so much the thermal efficiency of this sort of engine, but maximizing the work output given the temperature limits that are just reality. And so in order to maximize that work output, how do we calculate the sweet spot? How did it come out to 8.2? You know, that seems very arbitrary. So how do you come up with that? Well, it turns out to calculate the ideal pressure ratio for maximizing the amount of work produced by the cycle given temperature limits, all you need is the absolute value of the maximum and minimum temperatures to the exponent shown there based on the ratio of heat capacities of the particular working fluid, which in our case will always be air. And that is what generates the maximum work from the cycle given the temperature limits.